In the last class, we learned about the problem of PAPR, why PAPR has to be reduced, and from this class onwards, we will learn what are the techniques which are used to reduce this problem of peak to average power ratio. So I just wanted to revisit this equation for PAPR. Peak to average power ratio is defined as it is a ratio of peak power, that is maximum of x of n magnitude square. So it is a peak power among all the subcarrier points. The peak power comes in the numerator divided by the average power, expectation of magnitude of x of n square, which means the an average of power of each of subcarrier is considered, and average of power is taken. So this ratio, peak power divided by average power, it must stay within a limit. It should be at least equal to IBO, input back off ratio. Only then we can have a linear operation of the power amplifier. So in this class we'll learn certain techniques to reduce PAPR, and by just seeing this equation, you can think that PAPR can be reduced in two ways. One way is to reduce the numerator value, which means the maximum values of x of n, they correspond to the peaks of the OFDM signal in time domain. So you try to reduce the amplitude of those peaks, and methods which correspond to those are clipping and filtering, peak cancellation, peak windowing, etc. And another method to reduce PAPR is to increase this average power, and companding is one method which is used to increase the average power of FDM signal, such that PAPR reduces. So PAPR reduction techniques can be divided broadly into three categories. One is signal distortion techniques, where the actual signal is distorted. Like we just saw, there are methods in which the peaks can be eliminated. Peaks can be brought to a lower value, like some threshold value. The peak values can be brought down to some threshold value, and those methods actually they impose some distortion to the actual signal. We are abruptly reducing the peak value to some threshold value. So we are actually distorting the signal. Those methods correspond to the signal distortion methods. There are also multiple signaling and probabilistic methods where we are not distorting the signal. We are using some probabilistic techniques. We are using some signaling techniques in such a way that we are able to not to lose any information. So when you do signal distortion methods, that results in loss of information. But multiple signaling and probabilistic methods, they preserve the information content. They preserve the information content. And there are also certain coding methods by which you can reduce PAPR value. In our syllabus, we'll concentrate mostly on this signal distortion methods and multiple signaling and probabilistic methods. We'll see each of these topics in detail. Signal distortion methods reduce PAPR by distorting the transmitted OFDM signal. So when we say distorting, you should know that it results in loss of information. That is what you call distorting. Okay, loss of information. Before it passes through the power amplifier, this loss of information happens. We are distorting the signal in order to reduce the PAPR. PAPR can be reduced significantly to whichever threshold value you want the peak value to come down to. We are able to reduce the PAPR up to the desired level. But they introduce this in-band and out-of-band distortion, which leads to increase in bit error rate. So in-band distortion means within the OFDM signal bandwidth, this causes some distortion. Out-of-band is a distortion that happens outside the bandwidth. So when you have the OFDM signal in frequency domain like this, there are a number of subcarriers and you have the OFDM signal like this. In-band distortion is a distortion that happens within the band. So within the bandwidth. So this is the bandwidth of the OFDM signal, and the distortions that happen within the band is in-band distortion. And out of band is the distortions that happen outside the band. Okay, so this is the whole bandwidth of OFDM signal, and the distortions that happen outside the band, they are out of band distortion, or sometimes you call out of band radiation, out of band radiation, or out of band distortion. Okay, so when you have the signal in time domain, you sometimes will have peak values, you sometimes will have lower amplitude values, and this peak values, when you are abruptly clipping something like this, you are bringing these values down to a particular value, then in the frequency domain, uh, this will affect in spectral widening. Or in other words, it is nothing but the energy in subcarriers is spread to the neighboring subbands, or even it can extend even outside that. So energy of the power spectral density of of this subcarriers, it may spread outside its band, and it may extend to the neighboring subcarriers, disrupting the whole information, affecting the whole information. So if this spectral widening, or this the power leakage that happens out of the subcarriers, if it stays within the band, the power leakage which happens within the band, it's called in-band radiation or in-band distortion. And if the power is leaking out of the frequency, out of the band, it is known as out of band radiation or out of band distortion. And this out of band distortion can be easily eliminated if I have a filter which accepts only this range of frequencies. If I have a filter which accepts only this bandwidth of signal. This out of band radiation can be eliminated, but it is not possible to eliminate in band radiation because it happens within the band of OFDM signal, and it is very difficult, even though there are techniques which can reduce in band radiation, but in general in band radiation is more difficult to eliminate than out of band radiation. And due to this in band and out of band distortion, it leads to the increased bit error rate. So these are the common problems of all the signal distortion techniques. So you are distorting the signal, you are changing the shape of the signal. The high peaks are being brought to a lower value. So why is this distortion happening in frequency domain? The answer you can get very easily if you revisit the basics of OFDM. That is when you what is the reason for this peak value? It is basically addition of subcarriers, addition of n number of subcarriers. And why is this peak happened at this point is because the subcarriers had a common phase at that point. So when they had a common phase, a similar phase, they constructively added and resulted in this peak value. Obviously when you are changing the value of this amplitude, then this will correspondingly have an effect in the frequency domain. In general, we used to say abrupt transmissions, it results in spectral widening, right? Just like you can see a square pulse, which is in time domain. The frequency domain of square pulse, is a sinc function. Sinc function is infinite in bandwidth because there are abrupt transmissions here. So whenever there are these abrupt transitions from 0 to 1 and 1 to 0, whenever there are these abrupt transitions, we can observe that in frequency domain you will have a corresponding bandwidth which is close to infinite in nature. We'll see the most well-known signal distortion techniques. These are clipping and filtering, peak windowing, companding, and peak cancellation. So we'll see them one by one. First method is we are going to discuss is clipping and filtering, which is the most simplest technique, and also the technique which gives the not so good bit error rate. It is a simple method. It just means that it is clipping the high peaks of OFDM signal before passing it to power amplifier. It is basically this figure that I showed you. This signal has certain peaks and some threshold value. So this is some threshold value. So you want to reduce the peaks to some threshold value. I'm clipping level, so I'm naming it as CL. So if the signal goes above CL, above this threshold value CL, then it is brought back to this CL. Okay, so the new signal will look like this. So here all these values are below the clipping level, so no change for values which are below the clipping level. And when you have the signal value greater than the clipping level, it is brought back to CL. This peak value is brought down to the clipping level or threshold value. And when you bring it back, you should be careful that when you bring it back, it should not be abrupt. This phase should be preserved. So you bring it back like this. Okay, again signal values are preserved below the threshold value. Here again the signal is brought down to the clipping level. All right, so in this red color will show you the new signal after clipping. This equation it shows the clipping operation, and that is t of x of n, where this function t stands for clipping. The signal after clipping is equal to x of n if the value of the signal is less than the clipping level, and it is equal to clipping level, which means the signal is brought down to clipping level multiplied by its phase. The phase is preserved if x of n is greater than the clipping level. So that's the idea of clipping. And when we are doing this clipping operation, it results in this in-band and out-of-band distortion. Out-of-band distortion is filtered out using a filter. Okay, so while this both in-band and out-of-band distortion, they cause spectral spreading or spectral widening. Out-of-band radiation can be eliminated by filtering the signal after clipping. Okay, the idea which we discussed before. And this in-band radiation cannot be reduced by filtering. Okay, we need to do some other operations. Second method is peak windowing. You have learned about different windows in your digital signal processing. That is the Hamming window, Hanning window, Kaiser window. And peak windowing is about performing this windowing operation for the OFDM signal before passing it to the power amplifier. So it is not like peak clipping. In peak windowing, what happens is that the peak is reduced, but it is reduced by multiplying them by a weighting function called a window function. So this OFDM signal is multiplied by a window function. So the window may have different shapes. Different windows have different shapes, and so after multiplication, the peak value will reduce. And choosing the window function, it depends on which all spectral properties you need the window function to have. And these are the common windows: Hamming window, Hanning window, and Kaiser window. These are the common windows. And this multiplication of window function with the signal, it is done in such a way that the value of the window function, so the areas where the value of the window function is less, it is multiplied with the signal peaks. So we are multiplying the values with the signal peaks, so that when you multiply with a lower value of the window, the peak will reduce, and the higher amplitudes of window function, so like this, the high amplitudes of window function is multiplied by the lower sample values of the signal, right? So this action attenuates the signal peaks in a more smoother way, okay, when compared to hard clipping. The idea we discussed before, when you have abrupt transmissions, hard transmissions like this, that will result in infinite bandwidth. Always we prefer smoother transmissions. We want smooth transmission. That is the whole idea behind pulse shaping techniques. Why we use raised cosine filter, because they have smoother transition. This results in signal distortion, but we see that the distortion is less when compared to clipping. Third method is to use companding transforms, which have a relatively low complexity when compared to PAPR techniques. You might have learned companding in your uh, communication analog and digital communication classes. The idea is the same. We have certain functions called companding functions, companding transforms, and this signal is processed using this transform, and after processing with the transform, the signal will have a lesser PAPR. Of course, this method also gives some signal distortion to the original signal, but the advantage is that you do some companding transform in the transmitter side. You can do the inverse at the receiver side and get back the original signal. So you don't need to send any side information. Some techniques they reduce PAPR. When you are learning probabilistic techniques, you will know that certain techniques when we use that we need to send apart from the original signal or FDM signal, we need to send some side information uh, to the receiver, such that when the receiver receives the OFDM signal, they need to use the side information also to recover the original signal back. But the companding technique does not require side information to be sent along with the signal, OFDM signal. If you are doing companding transform in the transmitter side, the inverse of that transform needs to be done in the receiver side. So no extra side information is transmitted. And because it does not uh, transmit side information, it does not reduce the bit rate. Okay, additional data points are not required to transmit any side information. The companding transforms can be generally classified into four classes. One is the linear symmetrical transform, linear asymmetrical transform, nonlinear symmetrical transform, and nonlinear asymmetrical transform. I'm not explaining each of the equations and things like that. However, some equations easy for you to remember are, one is that of linear symmetric transform. You can easily see that it almost looks like a line, equation for a line. So x of n is the OFDM signal, where n ranges from 0 to n minus 1, and each of these points from 0 to n minus 1, they are transformed using this expression a into x of n plus b, and you get c LST of x of n. And you can see here LST is this line that goes like this. This is a graph which shows where x is the input signal, and um, the output of the transform is c of x. You can consider x as any variable, ranges from 0 to 1, and how the transform maps it in its axis. You can see that CLST, which is a linear symmetrical transform, it follows this line, and this V, the separation that you have here, V is some threshold value. V is some threshold value. When the signal crosses the threshold value, so it is a threshold value, maybe the value which you want to limit the peak of this signal. When the signal crosses the threshold value, signal amplitude crosses the threshold value, you can observe that this companding methods, it gives some effect for the signal to reduce the peak value. Sometimes it tries to reduce the peak value. Sometimes it tries to increase the average value of the signal, average power of the signal. Like we discussed in the beginning, there are two methods by which we can reduce PAPR. One is by increasing the decreasing the peak value of the signal. The other is by increasing the average power of the signal. Different transforms have different properties. Just by seeing this graph, we can derive some of its features. Here you can see LAST, linear asymmetrical transform. It almost follows a line from 0 to threshold value, and once the signal value crosses the threshold value, you can see an abrupt decrease of peak value. The amplitude has reduced considerably, and then again it follows a line, but it does not go over a particular threshold value. You can see that LAST tries to reduce the peak value of the signal, because after the threshold value you can see that a considerable reduction in the amplitude of the output transform. In NLAST method, which is this dotted red line, you can see that here from 0 to this point it gives somewhat okay linear, somewhat close to linear performance, and beyond the threshold value you have very less variation for the output transform. Here you can see almost the output follows the input, and beyond the threshold value you can see that very less change happen in this range. The output almost remains in this range, even though the input has so much of variation. The input varies from the threshold value to 1. The output is between this small range of values, which means that the PAPR is reduced. It is trying to reduce the peak value of the signal. There are also other methods like NLST, where this graph, which goes like this, you can see that the lower values has again it has less value for lower values, but higher values have slightly the changes again is evident here. Different methods, different transforms have different properties, and companding, whichever companding you use in the transmitter side, the inverse can be used in the receiver side in order to recover the signal. One of the important companding transform is using the Mu law companding transform, and it is different from these transforms. So these transforms, the speciality is that when it crosses the threshold value, it tries to reduce the peak value, but Mu law companding, it tries to increase the average power of the signal. You can see the equation here. This transform works according to this equation. The value x of n is transformed to xc of n using this equation. And in this graph, you can see two plots. One is that of uncompanded, and the other is that of companded signal. And you can see that this dotted line, which corresponds to companded signal, has more average power than the uncompanded signal. The peak values are preserved. The peak values are preserved, but peak values, they are preserved without no much change, but lower values, the values which are having lower amplitude, they are boosted. They are given more power. That's about companding transforms. You can refer to the paper I've sent you for more details if you want, if you are interested. This is the inverse transform of mu-law companding. And the last method which we learned in signal distortion methods is the peak cancellation method. The block diagram which shows peak cancellation is shown here. After the IFFT stage, there is a peak detector which detects the peaks in the signal. So if you have a graph like this, this is the original signal, and the dotted lines you see here, they are the threshold values. There are 2 points where the signal value becomes greater than the threshold value, exceeds the threshold value, and those are detected as peaks. So the function of this peak detector is to detect peaks, and a peak cancellation waveform is generated. Alright, a peak cancellation waveform is generated, and mostly sync pulses are used. Sync pulses are used as peak cancellation waveform. You can see that here. You can see two sync pulses. One is this sync pulse, and other one is this sync pulse. The places where there are peaks, they are identified, and sync pulses are generated at those points. And these sync pulses, they are subtracted from the original signal such that the peaks are reduced. The peak values are reduced. Okay, so that's about the signal distortion techniques. And in the next class, we'll see multiple signaling and probabilistic techniques. Thank you.